Hello everyone. I welcome you all to this seminar session. Let me introduce myself first. I'm Karthika from SCCT Palai, currently pursuing my electronics and communication engineering, and I'm a 7th semester student. Dr. Thompson Davis sir guided me on the seminar topic, ultra wideband antennas, and these are the contents that I intend to go through with in this session. So let's start. We all have heard about antennas at some point in our engineering life. An antenna is a transducer that transforms electrical power from a transmission line into electromagnetic energy that is emitted into space. Ultra-wideband, that is UWB technology, was initially developed with commercial radar applications in mind, and that was in order to provide high-speed bandwidth connections in wireless communication networks with minimal energy consumption. UWB communication uses short pulses and low power radio transmissions for transferring massive volumes of digital data over a broad frequency spectrum. UWB antennas are facing some challenges in terms of electromagnetic interference, signal path fading, etc. And to resolve these issues to a limit, multiple input, multiple output, that is MIMO antenna systems are being designed with UWB technology. Now this is a picture of a common antenna. An antenna can be called as an interface between radio waves propagating through space and electric currents moving along metal conductors. It can act as a receiver, that is, it converts electromagnetic waves from space into voltages and currents in a conductor, and also as a transmitter that can convert voltages and currents into electromagnetic waves. This is the reason why an antenna is called as a transducer. Antennas. They come in various shapes and sizes and are crucial components in wireless communication systems, including radio and television broadcasting, cellular networks, Wi-Fi, and satellite communication. Antennas work as per the same principles of converting electrical signals into electromagnetic waves for transmission and vice versa for reception, as you can see. And they play a fundamental role in enabling wireless communication across various technologies and devices. Now, coming to UWB antennas, as you can see, I have included an image of an ultra-wideband antenna, specifically a 2.4 GHz to 10.5 GHz pulse PCB antenna module. I only aim to familiarize you guys with an image, but keep in mind this image is not a general one. Now, what's an antenna? What is an ultra-wideband antenna? These are antennas that are designed to operate across a broad frequency range, typically spanning several gigahertz. Their range can be generalized from 3.1 GHz to 10.6 GHz. They are used in various applications including high-speed data transfer, radar systems, and location-based services similar to that of antennas. They are characterized by their ability to transmit and receive short pulses of electromagnetic waves, and this feature allows for precise time-of-flight measurements and high data rates. These antennas come in various designs such as monopole, dipole, patch, and horn antennas, and each are optimized for different UWB applications. Now coming to the history of UWB application. It first started in 1865 with James Clerk Maxwell's electromagnetic theory. Then on 1888, Heinrich Hertz's experiments, and in 1893, electromagnetic waves of Heinrich Hertz, and in 1906, the first patent for a UWB communication system filed by Lee D. Forrest, and in 1935, first UWB radar system developed by the British military. In 1940, UWB technology is used in various military applications in World War II. 1960, UWB technology is used in the development of new commercial products such as ground penetrating radar and medical signal imaging system, etc. Early 1970s, avalanche transistor and tunnel diode detector. 1972, short-range radar sensor. Late 1970s, narrow baseband pulse fixture. In 1890s, 1980s, advances in radar technology. In 1990, UWB technology begins to be seriously considered for commercial applications such as wireless communication and indoor positioning. From 1999 to 2002, the Federal Communication Commission, that is the FCC of US, allocates a 7.5 GHz band for UWB communication. In 2004, the first commercial UWB chipsets were released. 2005, the first UWB-based products were released. In 2007, the V-Media Alliance was formed to promote the adoption of UWB technology. In 2009, the first UWB-based smartphones were released. 2010, the IEEE 802.15.4 research standard for UWB communication was published. In 2012, the first UWB-based car radar systems were released. In 2014, the first UWB-based real-time location system (RTLS) were released. In 2016, the first UWB-based augmented reality (AR) and virtual reality (VR) headsets were released. 2018, the IEEE 802.15.4U standard for high-resolution UWB was published. 2019, the first UWB-based payment systems were released. 2020, the IEEE 802.11be standard for Wi-Fi 7 was published, and 2022, the first UWB-based access control systems were released, and from 2022 onwards, major advances are on their way. Now coming to the types of antennas. There are different types of antennas, and as you can see, I have classified based on geometry, radiation pattern, polarization, frequency range, antenna gain, size and form factor, and so on. So on the basis of geometry, antennas can be classified into biconical, bow tie, log periodic, spiral, and planar. On the basis of radiation pattern, it can be divided into three types: omnidirectional, directional, and multidirectional. On the basis of polarization, they can be divided into linearly polarized, circularly polarized. And on the basis of frequency range, it can be divided into three types: full UWB antenna, narrowband UWB antenna, and multiband antenna. And on the basis of antenna gain, they can be divided into low gain antenna and high gain antenna. Size and form factor, on the basis of that, it can be divided into compact antenna and large antenna. On the basis of customization, it can be divided into planar antenna and metamaterial antenna. On the basis of application, antennas can be divided into communication antenna, radar antenna, positioning and tracking antenna, medical imaging antenna, environmental sensing antenna, consumer electronics antenna, etc. Now this UWB communication. Ultra-wideband wireless communication is a revolutionary technology for transmitting large amounts of digital data over a wide frequency spectrum using short pulse, low-powered radio signals. UWB commonly refers to a signal or system that either has a large relative bandwidth that exceeds 20% or a large absolute bandwidth of more than 500 MHz. How UWB works? At first, the transmitter and receiver must be coordinated to send and receive pulses with an accuracy of a trillionth of a second. In a multiple access system, a user has a unique pseudo-random PN code. A receiver operating with the same PN code can decode the transmission. Now, let's see, why is UWB attractive? It has high head data rates. That is, UWB technology has a data rate of roughly 100 megabits per second with speed up to 500 megabits per second. And it has low power consumption. When transmitting data, UWB devices consume less than several tens of microwatt because the UWB transmit short impulse constantly instead of transmitting modulated waves. It has interference immunity. UWB has the ability to carry signals through doors and other obstacles that tend to reflect signals at more limited bandwidths and a higher power. It has high security. UWB has separate coding system that enables wide noise-like transmissions, which enhances security, since receivers without the specific code cannot decode it. UWB is limited to range. The output power is limited in order to keep down the noise floor due to its overlapping frequency bandwidth with other radio systems. 1 kilometer with high gain antenna and 10 to 20 meter with regular antenna. It is low complex and low costly. The cost of placing UWB technology inside a consumer electronic device is generally low. Now coming to the design parameters of UWB antenna, I have considered four major design parameters, which is the bandwidth, VSWR, efficiency, and radiation pattern. Let's come to each one in detail. Bandwidth. The first parameter that we have to consider for our design is the bandwidth. The bandwidth is basically the frequency or frequencies that the antenna is designed to radiate. In many cases, that is narrowband systems, the bandwidth specified for an antenna is very small because there is just one frequency that the antenna is required to radiate. In our case, we have to be able to radiate signals with frequencies between 225 MHz to 400 MHz. This required us to limit the antenna designs that we consider to strictly broadband antennas. Now coming to the VSWR. VSWR stands for the voltage standing wave ratio. It is the second parameter that we have to take into account for our design. The VSWR is defined as the Vmax by Vmin, that is the maximum voltage. This is the ratio of maximum voltage to minimum voltage. It can be calculated by using the equation 1 plus modulation of tau divided by 1 minus modulated tau. That is, the voltage reflection coefficient tau is defined as ZL minus Z0 by ZL plus Z0. Now, this ZL is the load impedance and Z0 is the characteristic impedance. This reflection coefficient is also equivalent to the scattering parameter S. The characteristic impedance is considered to be the impedance of the antenna for our purpose. The incident wave and the reflected wave V can also be related through the following equation for the total voltage on the line. V of Z is equal to V0 plus e power j beta Z plus V0 minus e power j beta Z, where beta equals lambda by 2 pi. The VSWR is a way of calculating how well two transmission lines are matched. The number for the VSWR ranges from 1 to infinity, with 1 meaning that the two transmission lines are perfectly matched. In regards to antenna design, a VSWR that is as low as possible is desired because any reflections between the load and the antenna will reduce the effectiveness of the antenna. Now coming to the third parameter, that is efficiency. The radiation efficiency of an antenna can be defined as E is equal to P rad divided by P in, where P rad is the power radiated by the antenna and P in is the power supplied to the antenna. The efficiency of an antenna is a measure of how much power is lost in radiating a signal from the antenna. Now the fourth parameter is the radiation pattern of the antenna. This parameter is highly dependent on the application of the antenna. In the case of the antenna design, the omnidirectional radiation pattern is better. This means that the radiation pattern had to be spread evenly 360 degrees around the antenna. That is how a omnidirectional radiation pattern works. The reason for this is because since the location of the transmitter is not fixed, you want to spread this radiated signal out as far as possible so the receiver will be able to pick up the transmitted signal. Now, let's see how the UWB transmission works. First, there are 5 steps. Let's go through each step. First one is the data encoding. The information to be transmitted is encoded into digital data, typically in the form of binary bits, zeros and ones. This could be any type of data, such as voice, video, sensor data, or text. The next step is the modulation. The digital data is modulated onto UWB waveforms. UWB signals are composed of very short, precisely timed pulses. Modulation schemes like pulse position modulation, PPM, or binary phase shift key, BPSK, are often used to encode the data onto these pulses. The third step is the pulse generation. UWB transmitters generate the ultra-short pulses that will carry the modulated data. These pulses are typically nanoseconds to picoseconds in duration, and they cover a wide range of frequencies as defined by UWB regulations. The fourth step is the antenna transmission. The UWB antenna connected to the transmitter radiates these pulses into the surrounding space. UWB antennas are designed to efficiently radiate over the wide frequency range associated with UWB signals. Now the last step is the propagation. UWB pulse propagate through the environment. Due to their short duration and wide bandwidth, UWB signals experience less fading and are suitable for applications like indoor positioning and object tracking. Now let's see how the UWB reception works. It also has 5 major steps. The first one is the antenna reception. The UWB antenna connected to the receiver captures UWB pulses from the environment. It's essential that the antenna is designed to receive a wide range of frequencies matching the UWB signal's characteristics. The second step is the pulse detection. The received UWB pulses are detected and processed by the receiver circuitry. The receiver looks for the arrival times and amplitudes of the pulses to reconstruct the modulated data. The third step is the demodulation. Demodulation is the process of extracting the digital data from the received pulses. The receiver uses the same modulation schemes used for transmission. That's example, if PPM is used in the modulation purpose, then in the demodulation phase, PPM is again used. Or if the BPSK is used in the modulation stage, then in the demodulation stage, BPSK is again used for the reverse modulation purpose. The fourth step is the data decoding. Once demodulated, the digital data is decoded to retrieve the original information. Error correction and error checking techniques may be employed to ensure the accuracy of the received data. The last step of the UWB reception is the data output. The decoded data is then made available to the receiving device or system for further processing or display. This could involve sending the data to a computer, displaying it on a screen, or using it for control or decision making. Now coming to the applications of UWB antennas. Wireless communication. UWB antennas can be used for high-speed, short-range wireless communication. They are employed in applications such as wireless USB, wireless HDMI, and wireless personal area networks (WPAN). UWB can offer high data rates and is suitable for multimedia streaming. Radar systems. UWB antennas are well suited for radar applications, including ground penetrating radar (GPR), automotive radar, and through-wall imaging. UWB radar provides high-resolution imaging and accurate target detection even in cluttered environments. For medical imaging, UWB antennas are used in medical imaging applications like breast cancer detection and microwave imaging. UWB signals can penetrate biological tissues effectively, providing high-resolution images without harmful ionizing radiation. The precision localization and tracking. UWB technology is used for precise indoor positioning and tracking. This is crucial in applications like asset tracking in warehouses, indoor navigation, and locating people in emergency situations. For industrial applications, UWB antennas are employed for level sensing and industrial tanks, object detection in manufacturing processes, and monitoring the movement of goods in warehouses. Their ability to work in harsh industrial environments makes them valuable in these settings. Now, environmental sensing. UWB antennas can be used for environmental sensing such as measuring soil moisture, detecting landslides, and monitoring structural health in buildings and bridges. Now, for automotive safety. UWB antennas are integrated into advanced driver assistance systems (ADAS) and autonomous vehicles for accurate object detection, collision avoidance, and vehicle-to-vehicle (V2V) communication. Now for security and surveillance. UWB technology can be employed in security systems for perimeter monitoring, intruder detection, and access control. It is also used in surveillance cameras for enhanced object recognition. Now, wireless sensor networks. UWB antennas are used in wireless sensor networks (WSNS) for applications like environmental monitoring, asset tracking, and smart agriculture. Their low power consumption and high accuracy make them suitable for these applications. Now, for law enforcement and search and rescue. UWB-based systems are used by law enforcement and search and rescue teams for locating hidden objects, people under rubble, or buried victims in disaster scenarios. Now, for communication in harsh environments. UWB antennas can provide reliable communication in challenging environments such as underwater communication for underwater vehicles, submarines, and offshore drilling platforms. For IoT and for smart homes. UWB technology is integrated into smart home devices for precise indoor positioning and improved context-aware automation. This enables applications like keyless entry, location-based services, and asset tracking within homes. Now for military and defense. UWB antennas have military applications for secure communications, ground-based radar systems, and electronic warfare. Now for agriculture. UWB antennas can be used for precision agriculture applications such as soil moisturing sensing, crop monitoring, and drone-based farming. Now for geological surveys. UWB technology can be applied in geological surveys to study subsurface structures and identify mineral deposits. Now the future developments of UWB antennas. It provides higher data rates, it is energy efficient, integration with 5G and beyond, miniaturization, enhanced precision, radar imaging, standardization, security application, medical and healthcare, environmental sensing, advanced antenna design, and mass market adoption. Now the challenges faced by UWB communication. Regulatory constraints. UWB operates across a broad frequency spectrum and regulatory compliance varies by region. Navigating the complex and evolving regulatory landscape can be challenging as different countries may have different rules and restrictions. Now, interference mitigation. UWB signals can potentially interfere with other wireless technologies such as Wi-Fi, Bluetooth, and cellular networks. Developing effective interference mitigation techniques is crucial to ensure coexistence with these technologies. Propagation characteristics. UWB signals are susceptible to attenuation and signal loss when they encounter obstacles or travel through materials like walls and foliage. Overcoming these propagation challenges, especially for indoor positioning and through-wall imaging, is a significant hurdle. Now, scalability. Scaling UWB technology for widespread adoption, particularly in IoT and smart city applications, poses challenges in terms of cost effectiveness and efficient network management. Now, in educational awareness. Many consumers and business are not yet fully aware of UWB technology and its potential applications. Educating end users about the benefits of UWB can be a challenge. Now, for market fragmentation, the UWB market is still relatively fragmented with different industry players promoting their proprietary solutions. Achieving industry-wide consensus and alignment can be difficult. Now, coming to the conclusion. The design and deployment of ultra-wideband UWB antennas is a broad and developing topic. UWB antennas are crucial parts of numerous cutting-edge technologies because of their propensity to function throughout a wide frequency band. And these are the major papers I used for reference for formulating this seminar topic. And with that, let me conclude my words and thank you.